So let's also begin to look at some of the issues these things face. Every time you make a change, you have to track many things. Obviously, everything has other consequences. So for example, proton exchange membrane fuel cells turn on and off like an automobile engine, and they're useful for operating these sorts of equipment and so on, forklifts, automobiles, heavy-duty trucks, and space vehicles, and for providing backup power in the event of a grid outage for servers and telephone cell towers and so on. And there is a process called reformation or reformation, where hydrogen is extracted from some fossil fuel or biofuel. So most commonly used one is methane, using a steam methane reformation process, or SMR, which we will see again and again. So when methane is exposed to heat and steam, the hydrogen can be separated and purified for industrial applications, as well as refining gasoline and make them high octane and so on. Okay, so the other concept that I mentioned already is the combined heat and power. So in a traditional setup, you give fuel to an engine or a turbine that is driving a generator to produce electricity for the buildings or facilities, or at a larger scale to a grid based on whether it's a utility scale central producer or a small turbine. And then the exhaust gases produced here are often used as heat recovery units to produce steam and hot power to drive additional cooling and heating required for the buildings or facilities. Okay, and new methods do combined generation. So they are the combined heat and power, or combined cooling, heating, and power. So here, instead of driving the boiler separately to drive the turbine, you mix the boiler with the fuel driving steam production and drive a steam turbine, and use the remaining steam and hot water to drive. So the temperature may drop enough that the steam becomes hot water, or based on the efficiency, it could still be plenty of steam left. Drive cooling and heating, as we saw in a separate circuit before, and electricity is produced as well through this generator as before. So this increases efficiency tremendously as opposed to the other one. So here is a figure from Veolia in the UK, which is talking about combined heat and power method with overall efficiency of 90%. So you have 100% fuel coming in, there are losses of 10%. You are meeting 50% of the power for with 50% of the power you're meeting heat demands, which has a 12% loss over there in terms of conventional method with the overall efficiency of boilers at 52%. I won't go into the details. I'm just trying to add this information which is not in the chapter. So there is fuel added there as well. So you are meeting 100% by losing 12% and gaining 62%. So 50 plus 62 and 12% loss will give you the operation of the boilers, and the power plant is meeting 40% of the power demand. Okay, so there is the numbers for fossil fuel input and losses. So you can see that the losses here are huge, whereas the CHP has efficiency of 90%. Okay, that's the idea. This is the so-called trigeneration, efficient electricity, heating, and cooling. We'll look at trigeneration in other contexts later on in terms of producing hydrogen, but nonetheless, I hope you get the idea. So instead of having separate units of driving turbines with fossil fuels and trying to use the exhaust heat for heating water and producing steam, you combine the two and increase the efficiency. The higher temperature provides both attractive options for combined heat and power or combined cooling heat and power, and the ability to internally reform the fuel, for example, natural gas. Okay, the technology has led to operation of fuel cells on biogas, so you can use the heat to drive SMR, like steam regeneration of methane, steam methane reformation, so sourced from water resource recovery facilities. Okay, these are where wastewater or used water is being recycled to produce usable water again. Generation of carbon neutral hydrogen as well as electricity and heat, referred to as trigeneration. Okay, so here you could have heat generation for boilers, or you could be driving steam methane regeneration to produce hydrogen. So this is just a schematic of a water resource recovery facility of the future. This is from EPA, I think, or somewhere. I picked it up. It's not written over here. Sorry about that. So there is the utility, which is driving various processes, so integrated production of clean drinking water, other water grades, healthy aquatic systems, fuels, electricity, chemical, fertilizer, and so on. And the outcomes of such a system, which combines the water recovery facility with other uses and generations. So there are smart systems communicating with sensors, software, and advanced devices that monitor volume and content of incoming steam streams, inform plant operations, track performance, and verify output safety and quality. Okay, the outcomes, of course, are that there is healthy environment, renewable energy supply, reduced carbon emissions, economic growth, vibrant and greener communities. So it's not just about how power is generated and how transportation is merged with electricity, but also to think about how the power generation and the required fuels like hydrogen are being produced by combining with water resource recovery equipments. Okay, so smart cities, for example, can combine these kind of methodologies where local distributed energy generation with local generation of hydrogen battery, as we called it, with smart buildings, entire city operating as a smart city, etc., can really begin to reduce emissions and eliminate emissions in the future with these kind of fine controls.